Hello. In this presentation, I'm going to talk about optical intelligence and how it supports and is critical to achieving key improvements in optical network operations performance, automation, and improvement of network efficiency. The synthesis and use of actionable intelligence generated by machine systems is the key to automation. The now well-established automation process loop has four parts: data collection, data analysis, decision-making based on analysis-generated intelligence, and actuation of decisions. In the case of optical networks, the key actionable intelligence to be generated from analysis of network data is optical margin. Margin tells us how far from performance limits an optical connection is or would be, and also, effectively, how much latent capacity is available on that channel and network. Accurate knowledge of margin is not something operators traditionally have had, particularly in a predictive sense. And this has had significant ramifications for optical network operations, constraints, and costs across the board, from planning and control to provisioning, protection, and fault minimization and preemption, as well as on infrastructure efficiency and CapEx. As an example, in Huawei's implementation, optical margins are calculated using an analytics application we call OPE, for Optical Performance Engine. This cloud-based engine is part and parcel of the analytics suite of our iMaster NCE control and management platform. OPE assesses many individual optical transmission performance metrics, such as linear OSNR, nonlinear noise, and impairments due to optical filtering. But available margin is the key final result. To encompass all use cases and applications, the OPE must be able to deliver results on a high volume of hypothetical future network configurations, as well as provide ongoing and comprehensive actual margin evaluation. Its compound models are complex, the more so the larger the network, even if the constituent component models are less so and bounded in number. It supports interchange of inventory, topology, and service information with NCE and associated applications, and access to the large volume of changing instrumentation information collected from the network. It is accessible by both NCE internals, e.g. for control operations, and applications designed to interwork with NCE, e.g. planning. The OPE should be understood as making use of various atomic models, some of which are delivered by machine learning. The most important of these models is for gain and noise figure of EDFAs. These are accurate models specific to amplifier type and even instance. We have described our developed methods for accurate EDFA modeling in past publications. Various other models and point of manufacture data complete the suite of capabilities needed to deliver margin assessment. In some cases and circumstances, directly measured parameters may be used in place of model-generated parameters. This is desirable where it is possible, as it may enhance the accuracy of margin assessments. Network-based instrumentation and models thus work flexibly together. It is important to point out the distinction between margin evaluation and margin prediction. Margin evaluation means estimating the margin available on active operating transmission services, i.e. with the optical network in its actual configuration. This indeed requires some analysis on top of what may be measured, particularly on top of what is generally measured in legacy networks, as the complexity of the evaluation may be reduced and its accuracy improved by proliferating more and new types of instrumentation in optical networks. But it is a far more constrained problem than margin prediction, which answers the question, what would be the available margin on transmission connections, new connections and remaining ones, if the network configuration and conditions were to be changed? Many use cases of greatest impact and interest demand a margin prediction capability. Various applications will call on a mix of margin evaluation and prediction capabilities. The OPE always uses the best available information from inventory and network operational measurements to support its calculations. For example, a greenfield planning exercise might have only nominal fiber lengths and types to support linear and nonlinear noise assessments, but it can use specific amplifier type models. A brownfield planning exercise would use some such data, but could also use real performance information, such as actual fiber losses and nonlinearities from the currently deployed network. Real-time control operations, e.g. to support dynamic network provisioning, would have even more actual network information to work with. The OPE is conceived to be able to handle all of these application types and more in parallel operation. By way of example, we describe two specific OPE-enabled applications. The first application is the continuous reporting of available margin on operating transmission paths. This draws on the margin evaluation capability of OPE. Derived functions include tracking the margin evolution history on operating services and the provision of alarms indicating services on which margins have dropped below settable thresholds or in which trends indicate an imminent or near-term degradation of service. The utility of these capabilities needs no explanation, but it is worth noting that they allow for fault prediction even in operating regimes where no bit error counting and extrapolation or similar measures can function. Various fault management applications supporting prediction and preemption of some faults and interpretation of transient degradations, whether directly observable at the service level or not, can be built from this capability. The next application draws on the margin prediction capabilities of OPE and relates to channel add-drop operations. The idea is to predict accurately, that is, in advance of executing the prospective operation, the power and OSNR and margin implications on all channels post-operation, that is, both added channels and existing channels. This information distinguishes safe from unsafe provisioning or reprovisioning operations. And batching and sequencing determination algorithms built on this information can optimize operations for execution speed and integrity. All of this can directly underpin potential automation of provisioning operations. Many more use cases, including some related to the assurance of dynamic protection schemes, are enabled by predictive margin assessment capability. We will say more about this in future talks. But where functionality like that provided by OPE can really strike hard is in the general area of network control and planning. In a world of flexible transponders, what we call RMCSA for routing, modulation, spectrum, and coding flexible allocation. Finding the most efficient resource tuning and allocation solutions on a network is an optimization problem, one that is very difficult absent pseudo-heuristic algorithms or similar that are able to quickly find such solutions. Finding such optimal solutions leveraging flexible transponders allows transmission capacity and distance allocation trade-offs to be made according to service traffic demands. In the optimized result, enhancing the effective total capacity distance product of the deployed assets and reserving more effective capacity for protection and for incremental service requests. As suggested here and in the results at upper right, our work indicates that significant benefit is available on large, that is, regional to super-regional and mesh networks. In some cases, expressed in terms of gains in usable network capacity of as much as 40%. These gains can be further enhanced by using predictive margin assessment in replacement of fixed and necessarily conservative reach tables, squeezing margins, and expanding further the service traffic bearing capacity of the deployed assets. Further, the optimization can be run continuously and the actuated service configuration modified where required, as OPE or similar takes account of changing margin conditions across the network. These kinds of network optimization capabilities require not only margin prediction, but ongoing and high volume configuration-cased margin prediction capability. The nature of models used and the architecture of the OPE or OPE-like software architecture become critical. And this is part and parcel of what I personally call dynamic margin management, a topic that has generated much interest across the industry. There are various ways in which margin management or compression can be applied in practice to contribute to resource and capital efficiency. One could first move from the historically normal large, blindly set static margins to periodically reset tighter margins. This allows greater transmission capacity and/or transmission distance allocations to be made, enhancing the total capacity distance product of the deployed assets. One could, over time, increase the frequency of resets and decrease the margin reservations at any point. Note that these actions and principles can be applied to both primary and, dynamic or not, restoration facilities. But one thing must be stressed. In the absence of a high-performance margin measurement and margin predictive analytics engine, real margin management, especially in aggressive margin management regimes, real-time control scenarios, and tending toward automation, simply cannot be achieved. I hope that this look at a particularly important optical intelligence capability, margin measurement and particularly margin prediction, has shown what improved operational and capital efficiency impacts may be enabled as optical networks become larger, more meshed, support higher transmission volumes, and tend toward greater direct service utility, which will bring increasing call for dynamic service provisioning. Thank you.
Thank you, Christopher. Thank you. Let me remind participants to please put questions into the chat. Okay, so we have a question here from the audience. The question: the digital twin is used to simulate the real network alterations. Who is the user? Is this offered to automate upper layer of the network? And if so, or is it limited to the transport layer? If offered upward, is the interface standard or standardizable?
Yeah, so good questions. As I said, in our conception, this is an analytics engine that is part and parcel of a suite of such engines that are architecturally part of our control and management platform. So the questions, the ability to interrogate the engine and receive the answers belongs to the control engine itself. So you can imagine for real-time control purposes, for any processing of fault-related information that may be directly resident in that platform. But of course, it's also available to any applications that work on top of or with the control and management platform, right? So for example, or a key example I gave is a planning application that would, well, there's different permutations here, but if you imagine a brownfield planning application, for example, one that might be in the hands of the operator itself, they would be able to explore scenarios for network change and evolution. And basically it would work with the deployed NCE engine. And basically there would be flow through capability to interrogate the OPE engine and provide information to it and receive the answers. So obviously that kind of thing does transpire over a northbound interface. Now, in terms of standardizing those interfaces, of course, that's something we're all on board with, but this kind of capability is well ahead of where the standards efforts are focused, right? I mean, it's taken a long time, whether it's TAPI or ACTN and IETF, to get the abstraction models for provisioning and advanced provisioning applications like slicing that are sort of core to what those superior layers want to do. So that's kind of where the effort focus has been. In terms of being able to progress beyond that to this kind of ability to interact with proprietary analytics engines that may be in different controllers, that's obviously a much more complex problem. Frankly, I don't see that happening anytime soon. But certainly any given vendor that has capability of this type can provide their own interfaces. Those can be documented for a customer. But standardization is always a longer path than innovation, right?
Yeah, that's good.
And beyond that, really the models that are intrinsic, right? They may have some vendor dependence, and this is one of the big things that people working in open optical systems, I think, understand pretty well. That if you're going to try to plan systems that involve parts from multiple vendors, you do need models. You do need to be able to try to model performance of the network and the configurations you're trying to plan. But your ability to do that well is constrained by the quality of the models, right? So far, standards efforts have sort of looked at, well, what are kind of standard EDFA models, but they know they're only going to be so accurate. Whereas, if you construct a library of models that are specific to amplifier or other equipment types, they can be much more accurate. So in a sense, where you're really trying to build large, complex, high performance optical networks, it seems very likely you're going to be able to do that in a more restricted vendor environment for quite a long time. But part of the decision point here is, I think, how complex and near to optical performance engineering edges are you going to be, right? That answer differs from network case to network case.
Right, exactly. We have another question for you. How does the margin vary in a system operating under normal operating conditions over, say, a daily cycle? And how large are the changes for events such as unexpected loss of channels?
So I would say we see three things that drive evolution in margin. One are sort of long-term trends, right, where you have various types of fiber plant degradation, and that's everything from aging to increasing degrees of loss at connector points. Then you have your sort of time-based variations driven by things like temperature, diurnal, or other. I don't want to give you numbers, but these variations can be significant. Then you have point effects from potentially severe weather disturbances or let's call it mechanical events that might affect the plant or the equipment. Part of the value, of course, is being able to study those trends and kind of separate one from another. And even if you don't know root cause, you can sort of, you can imagine even just a time-based analysis to try to pick apart the different trends and try and see what's on a trend to potentially be disturbing, and if so, on what time frame. And of course, on the third category is provisioning operations, right? Every time you you change the loading on optical amplifiers. And of course, this gets more complex the more meshed the network is, right? It's a constrained problem on a series of disjoint point-to-point paths, but on a mesh network where you have sort of a continuum of degree of sharing of paths, every time you change the configuration, you change the loading, and you can in fact move both the power and the SNR fairly significantly on different paths. So it's something to be very aware of and to try to model very well if you want to, at least if you want to get past the allocation of very large margins simply because you don't know where the margin edge is. It's something you have to calibrate well.
Right, right. Okay. Well, Christopher, thank you. Thank you very much. Very nice presentation.